Which way does the compass always point?
North is what they say.
Okay, so that's correct. And it points to the North Magnetic Pole. That thing that's pointing there is the North Pole of the compass needle. The compass needle is itself a magnet with a North and a South Pole. Now here's a little known fact, okay? What can you tell me about North and South Poles of a magnet?
That
Take two magnets together, what do they do?
well, they repel each other if it's the same pole.
Which repels? Which repels?
So north to north and south to south.
They each repel each other.
They repel
correct?
each other, right?
The
Yeah.
like charges repel.
Right.
So wait a minute. If the needle of a compass that says north on it points to the North Pole, shouldn't it be pointing in the opposite direction?
Right. It should be repelled and pointing down.
Okay,
south.
except it's not. It's attracted, which tells you that Earth's south magnetic pole is in the north. Because the north part of all magnets point in that direction.
Okay.
Okay? That the Earth's south magnetic pole is in the north, which is why all north poles of magnets point there. All right, so here's what happens. We have a magnetic field because our core is fluid. All right, all the heavy stuff when Earth was molten, the heavy stuff fell to the middle. And the heavy stuff is the iron. And the light stuff, which is the rocks, floated to the top. Okay? And we don't think of rocks as light, but it's much lighter than metal. All right, and so all the metals, nearly all the metals went to the core. Some got frozen in place, and so you have these ores, these veins of ores. As Earth is solidifying, it didn't fall down fast enough, and it got frozen in place. There are other occasions where volcanoes can redistribute material from below and put it up in the crust. But basically, most of Earth's iron is in our core. And it's hot. And so the iron is molten. And when you have molten and you're spinning, you have moving magnetically chargeable metals. Okay? Iron is magnetizable. When you have moving metal, you create what's called a dynamo. And in a dynamo, you basically create a magnetic field from scratch.
Wow.
That's why old dead planets that have cooled do not have magnetic fields.
Right. Wow.
Okay? They don't have magnetic fields. Like Mars, no magnetic field to speak of. Okay? Because it's cooled faster than Earth did. It's smaller, so if you're smaller, you will cool faster. And so, no, you don't have this churning. By the way, Mars once did, for sure. Mars has the largest known volcano in the solar system. Okay? So Mars used to be hot on the inside, but that's called Olympus Mons. All right? It makes our volcanoes look like molehills, by the way. It's huge. It's huge. So, anyhow, the point I'm getting at here is the dynamo goes through cycles.
Okay.
And it goes stronger, then it goes weaker, and it flips.
Gotcha.
And so every 500,000 years or so, the magnetic field of Earth has flipped. Period.
Okay. That's pretty wild.
Okay? Yeah, it's fascinating. And while it's flipping, it actually goes to zero and then recovers coming out the other side. Different bands of the electromagnetic spectrum tell us different things about the universe. So if you're going to do that, you need telescopes that specialize in the chosen band. And by the way, we didn't even know light came in bands other than visible light. Somebody had to discover that. I mean, just think about it. Why would you have any inkling? Why would you believe at all that there was a kind of light out there that your eyes could not detect? So there's certain expectations of who and what we are as a life form that were completely overrun the day infrared light was discovered. William Herschel discovered it, and how did he do it? He knew that Isaac Newton figured out that white light is composed of colors. And he had the foresight to ask the question, I wonder if the different colors of light have different temperatures.
Yeah,
Just to even ask that question. I mean, just
Pretty impressive question.
think about that. It's a simple question, maybe retrospectively obvious, but at the time, okay, so what does he do? He has a thermometer and puts it in each of the different colors of light. But wait a minute, you need a control thermometer. So he took his control thermometer, put it off to the side, just to the side of the red. Okay? So that was not in the spectrum. All right? And that would presumably just measure room temperature. All right? But it was still on the table where he was measuring the rest of the temperatures. Your control has to have a minimum of variation other than the one thing you want to change. Okay? So the thermometer's on the table, but just off to the side. And so there he is, he's measuring the temperature of blue and red and yellow. And what he's finding is that the thermometer off to the side is consistently measuring higher temperature than all the rest of the thermometers, all the rest of the readings that he was taking. And he said, WTF. I'm sure that's what he said, okay?
Yes, exactly.
I am sure.
And right after that, he went, OMG!
That's
OMG, WTF!
all right. So he publishes this paper, and it's beautiful in how he's tiptoeing around a discovery because he doesn't really know. He said, could there be light that is unfit for vision?
Unfit for vision.
This is how he described it.
That's a great description.
And he does this enough, and I think I've discovered light unfit for vision. You're damn right you did, and it's light below the red, and what do we call it? Infrared.
Wow.
Okay.
And it's so funny, you still see the hubris of human existence there. It's unfit for vision, not we can't see it.
We blind to this
Right,
thing.
exactly.
It's got the problem.
It's got the problem. Not
It's
us.
unfit for us.
It's unfit for vision.
I hadn't thought about it that way. Very good.
Yeah.
So it turns out, so that's just an interesting sort of discovery experiment. And then we would learn, well, if that exists, maybe other bands of light exist. And so thus, thereafter, we would discover ultraviolet, microwaves, radio waves, X-rays, and they each have their moment in the sun, so to speak. And that fills out the entire, what we call electromagnetic spectrum. Only a small fraction is visible light. And so now you're going to say, what in the universe gives off infrared light? And you find out that things that have kind of any temperature at all will radiate in the infrared. Okay? Now, so for example, if you have an electric stove and you put it on low and turn out all the lights, can you see it? No. Not if it's on low, but you put your hand on it, you'll burn your hand. Okay? So
Tell me about it.
something is coming out of the stove and it's not unfit for vision, right? It's infrared light. Okay. And when the thing gets hot enough, it's not only giving off infrared, it'll begin to also give off visible light.
Right.
Okay? But if the thing is cool enough, it's primarily only going to be giving you infrared. Suppose you want to see infrared. All right? And by the way, infrared doesn't make it very nicely through Earth's atmosphere. You know how you know this? Because we have greenhouse gases that trap the infrared that is down here. Okay? Right. So the greenhouse effect are molecules that have a special relationship with infrared. And there's the ground trying to radiate infrared back into space. It said, no, you don't. And it sends it back down and accumulates. Okay. All right. This has been Star Talk. Things you thought you knew. Neil deGrasse Tyson, keep looking up.